will show the lower bound, of sorting algorithm, where this sorting is based on comparisons. Means when you will sort the numbers, then you will compare whether AI is greater than AJ or AI is less than AJ, like this. So examples you know already, that bubble sort, quick sort, merge sort, selection sort, all of these are based on sorting the numbers in the array. But in case of radix sort, for example, you do not compare whether which one is greater, these or this. Those who knows, you can check that it is, we just see the bit positions, not the do not compare the number. Now lower bound means what will be the minimum amount of time to required for sorting a list of numbers. So that is n log n, big omega of n log n. It will be at least n log n. So we have to prove it. And if you, why lower bound is very important, because if you know the lower bound of sorting, for example, sorting, in case of sorting, lower bound of sorting is n log n, and it has been proved, then you will not waste your time to design an efficient algorithm whose time complexity will be less than n log n. If you try to reduce the time complexity of any sorting algorithm to less than n log n, you will be failure, because it will take at least n log n time, lower bound. Now how to prove this? So here we prove it using decision tree model. Okay, decision tree model. So suppose this is the array A. Array A is say A1, A2, A3, AN. There are n number of elements in an array, and we need to sort this. So for this, we will compare the elements and we will get some. So basically in decision tree, what happens, uh, in internal nodes, we compare two element, AI and AJ. Means AI may be less than equal to AJ, or AI may be greater than AJ. These are the two possibilities. I am writing just I equal to less than equal to J. I have merged these two conditions. So these are in the internal nodes of the tree. Internal nodes contains two item AI comma AJ, like this. So how does it looks? So suppose I am taking for a small example, I am just taking uh, 3, 1, 2 and 3. These three elements, suppose only these three elements are there, I need to sort them. I have taken a small example. Sort the array A. So at the root, what I will do, internal nodes are represented by circles. Okay. So in this case, A1 comma A2. Okay. So, or better, for simplicity I am writing like this: is A1 less than equal to A2? There will be two branches. I am writing this big, should be bigger. Is, so there will be yes and no. Now, if it is yes, then I will compare. For example, is this is the question mark actually. Is this? So here is A2 less than equal to A3. So here I will get yes and no. So if it is yes, you check. If it is yes, then I will get an output. The order is A1 in this path. You check A1 is less than equal to A2 and A2 is less than equal to A3. So what will be the sorted order? This will be the output A1, A2, then A3. This is the output rectangle. Fine. But if it is no, means in this path, you see, here I am going, and in this path, what happens? A1 is less than equal to A2. Okay. But A2 is greater than equal to A3. In this path is what? It is no, no, this is no. No means actually A2 is greater than A3. And I know that A1, A2 is also greater than equal to A1. You check it, this path. So that means we need to compare now. A1 means we know that A2 is greater than both A3 and A1, but we do not know anything about A1 and A2, which A1 and A3, which one is greater. So what we shall do, we will compare A1 with A3. So here yes and no. So in this case, you see what happens. I know that A1 is less than A2 and A2 is less than A3. So therefore, I will get an output this A1, then just a minute, A1, A3, A1 is less than A3, yes, A3, then A2. So this will be the output. And if it is no, what will be the result? Tell me the sorted order.
A3, A1, A2.
A3, A1, A2. So this is the output. Now come to here. In this case, if it is no, so no means actually here we have A1 is greater than A2. So here I am comparing just this. Say A2 is A2 greater than A3, or if you are thinking that I means uh, I will represent in this way, means less than equal to, then you can change also it. Is A3 less than equal to A2, like that. Okay. So now what happens here? Here A1 is greater than A2 and suppose A2 is also greater than A3. So I will get in this case A1, A2, A3. Similarly here, what you will do, if it is no, then tell me what, if it is no, then here A1 is greater than A2 and A2 means A3 is greater than A2. So I should compare A1 and A3. So if it is so, then I will get one output. I am not writing, so you can complete it. Okay. So A1 is greater than 4, or you can check A1, A3. In this case, it will be A1, A3, then A2. Otherwise, it will be A3, A1, A2. Now, our objective is not to draw this figure, actually to tell you that you see an interesting fact that if you sort, the items in this, then either you will follow, means depending on the input, either you will follow this path, you see, and you will get this, or you may follow this path and you will get this thing, or you may follow this path and you are getting this. Similarly, depending on the numbers, you may follow this path, or you may follow this path, or you may follow this path to get the output. So all these are the outputs. Fine. Now, how many outputs are there in this case? How many total? How many possible? Six.
Six.
So if three elements are there, this six. If n elements are there,
N factor.
Real, sir.
factorial n, because we know that arrangement can be, means there can be factorial n permutation of the numbers. So that if we sort the numbers, then the sorting series, after sorting, the output will be one of the permutations of all the numbers. So factorial n, fine. And you tell me, what is the time complexity here? Time complexity means, time in this figure you see, the time complexity means in this case it is denoted by which factor? The height of the tree. When you are sorting, means you are comparing the numbers. So if you are comparing the numbers, then which, so for example, suppose this is the output, for example, this one. So you are following this path, this path. So that means its height will give you the how many comparisons of the data are required. Is it clear? How many nodes? You here see, you are comparing here, you are comparing here, how you are comparing here, fine, and even then you are getting this. So automatically the height of the tree gives you the complexity. In worst case, I am taking this longest path. Other case, here only two paths. See, only these two nodes you have to compare. But depending on the inputs, you may have to compare more number of times. So similarly, there can be a factorial n leaves, and whose height will give you the time complexity. So therefore, I can write time complexity Tn, that is denoted by the height of the tree. It is measured by, better I should write, is measured by this. Now, what is the height? Let height be the h. So h is, you already told that how many leaf nodes are there. So letter n is the number of elements in the array, and you told next number of leaf nodes is equal to factorial, sorry, is equal to factorial n. Now, what is the height? Tell me. Height is, you know already in data structure.
Sir, log n.
Log log of the number of leaf nodes.
Yes, sir.
Okay, number of leaf nodes.
Log n factorial, sir.
Log, yes. So that will be log of this. Now we can write these as log n into n minus 1, n minus 2, say n by 2, three, 2, 1. Just factorial n. I have written it like this. You know, n into n minus 1, n minus 2, dot, dot, up to 1 in the expanding form after expanding. So this portion here you see is greater than equal to log of, here you see that n is greater than equal to n by 2. Is it not? This term
Yes, sir.
n minus 1 is also greater than equal to n by 2. This term is also greater than equal to n by 2. I am writing this and I am rejecting this portion. I am ignoring this. So automatically this multiplication will be greater than this. So log of this will also be greater than this. Now what is this value? Whole to the power n by 2.
Yes, sir.
So you know this is the base 2 automatically. Why I forgot to this? Because every, you see,
Has two nodes, sir.
two branches.
Two branches.
Fine. Two branches, fine. You can write here that this is an tree, in this is an tree. Each internal node has two branches. So these two is actually here. So this is, now come to here. N by 2 comes here, log. Clear? So log A by B is log A minus log B. So that is equal to n by 2 minus 1. Now this is the Tn. You check it. H. H is height is of the order, this Tn is determined by H. That's H. So therefore, now I think you can prove that this expression is greater than equal to some constant into, you see, n log n is there. It is what? N log n base 2 automatically by 2 whole divided by 2 minus n by 2. So this expression is greater than equal to c into n log n for all values of n greater than equal to n naught. Means you can find out that I am not saying you or your friend may get some different value of c and n naught, but you can find out c and n naught. What will be the c and n naught? That you can find out. But you can prove that this Tn is greater than equal to this for all values of n. But please do it, complete it. Okay. So that means the lower bound of sorting is yellow. Okay. Now, just I am not going to start the another means algorithm for different problems, but before that, I am just means in next class probably I will say something about that. But convex hull is there in your syllabus also. So, what do you mean by convex hull? Just at least you should know the definition now. Convex hull of a point set P. What is P? P is small p1, small p2, p3, dot pn. These are the point sets. So that means suppose these are the pins stuck on a board like this, and what you will do, you take a rubber band, tight rubber band. This is tight rubber band. So if you take the tight rubber band, what will happen? If you release it, it will shrink. It will shrink in this direction. This will shrink if you release. So if you release it, it will shrink, and it will take the shape of what? It will take the shape of like this. Take it.
So shrink, if you release it means, sir, like it encapsulates the that polygon that you drew around the
No,
extreme
no.
points.
This is the rubber band, tight rubber
Yes.
band, and these are the pins that you have inserted in a board. Okay.
Okay.
So
Yes,
if
sir.
you release the rubber band, just release, then it
Yes,
will.
sir.
And this is a tighter. It is expanded. Okay.
Yes, sir.
Yeah. So it will try to sink, and it will. But
Yes, sir. Yes, sir. Yes, sir. Take that shape, sir.
yes, that it will take that shape. So this is called the sorry. This is called the this is called the convex hull. It is denoted by CH sometimes of the point set P. Clear? So, or in other words, what do you mean by convex hull? That is another definition. So, but before that, do you know the difference between convex polygon and non-convex polygon?
Yes, sir. Internal angles of a convex polygon are not reflexive, and non-convex is reflexive, sir. They might be
Yes.
reflexive.
So that means here you see, suppose just I am again repeating if anybody has problem. This is a one polygon. This is another polygon. This is also, these both are, this is polygon, this is also polygon. Now the definition says if within a polygon you take any 2 point, at any two positions, no problem, and you connect them by a line segment, then that line segment will not intersect the boundary. But here you see, if we take 2 points, suppose here and one is here, and if we connect them by line segment, then it is intersecting the boundary. So it is non-convex polygon. This is non-convex, and this is convex polygon. Now, what C is saying, he is saying that, you see, in this case, all these internal angles, you check all the internal angles, and here also. In figure 2, in case of all the internal angles are less than 180 degree. And here, one angle, for example, this angle is greater than 180 degree. Okay. So this is the difference. Now, what do we mean by convex hull of a point set? So there is another definition. Convex hull, you already know that these are the points. Now, if I ask you to draw a convex polygon that covers all the points, you may draw like this. For example, one of your friend may do like this. This. So there may somebody may draw like this also. This is a convex polygon that covers all the points, okay. So now we are interested to find out the convex polygon that covers all the points. Not only this, but also its area will be minimized. That means its area will be minimized only in this case. You see, this. Okay. So here, this will be the convex polygon. Sorry, convex hull. It is the convex polygon that contains all the points and of minimum area. Clear? So this is the definition is clear now.
Yes, sir.
Now I am asking just last question, one, that suppose this is the convex polygon. Now if I draw external point outside, we draw a line. Is it tangent to this convex polygon P? I am asking.
Sir, repeat the question once, sir.
Is it tangent?
Which line, sir? The line you just drew.
This is the convex polygon, and this is
Yes, sir.
P2V2, PV2. This line, tangent. Is it a tangent?
No, sir. No, No, sir. It's not a tangent, sir. PV2 is not a tangent, sir. P Sir,
Is it tangent?
sir, PV2 is not a tangent, sir. PV4 is a tangent, sir.
It is not a tangent.